Hi everyone, and today I'm proud to have Swarna talk about his work on continually learning planning agent for large environments using LLMs and state space graphs. So basically, I met Swarna at this IEEE CAI conference on artificial intelligence this year, and his work impressed me. Like out of the many posters, I only stopped for two or three. His was one of them, and it's basically a way for agents to use knowledge of what they have learned in the form of like a state space graph and doing some planning so as to improve performance. And he achieved state-of-the-art performance at this environment called ScienceWorld. So I leave Swarna to explain more of his work, but I would like to say that Swarna and I share very similar interests. We are trying to make agents become fast learning, adaptable, and we are learning it through various different priors and knowledge. And so it's very interesting to learn from what he has to share today. So without further ado, Swarna, please.
Thanks, John. Thanks for the intro. So as John said, I'll be presenting one of the agent that I have created. So it's basically a planning agent, uh, mostly intended for solving large environments. And I have combined the state space search and LLMs and reinforcement learning in a certain way to solve these large environments. So maybe I'll just reduce this. Okay. So what is planning? So it involves choosing a sequence of actions that will transform the state of the world step by step so that it will satisfy the goal. So basically in planning, we are given a certain goal. Let's say an example, like I invited John to my house and John wants to visit Swarna's house from Singapore to India. So that's a task. It's a goal. Now, in order to complete this task, so John needs to plan it out, like how he can travel from Singapore to India, from his house to my house. So probably first he has to take a taxi to go to the airport, and then probably he has to buy a ticket in the airport from Singapore to Kolkata. And then after arriving to Kolkata, he has to again probably take a taxi and travel to my house. Now, there can be a lot of different options at different states. Let's say John takes a taxi and goes to a post in Singapore, and he can take a ship and he can travel to another post in India, or he can take a flight or airport from a airport. So at each different state, so there can be a lot of different actions possible. Now, John has to choose the suitable set of actions that probably should be optimal in certain way. Like it might be less costly, it might take less time, it might take less effort, and it will satisfy the goal. So that is all about planning. So we need to find those set or sequence of actions that would satisfy your goal. Now, most of the works on planning use a state space transition system model. That means the environment is modeled as a state space system, and the world may contain the model may contain finite or infinite number of states, and there are certain actions possible within the environment, and each action will change the state of the world. So let's say you took action to travel from one place to another by taking a taxi. So of course that will change your state. Like you are in a one place and you took a taxi and move to another place, your state got changed. So this is how our environment should also be modeled in a computer system. So environments can be, of course, of different types. So some of the popular environment, like modeling of environments, can be Markov decision process, like MDPs, or partially observable Markov decision process. So Markov decision process is like your next state is dependent only on the previous state and not the states before. So this is done to model the state space planning. I mean, to make it easy to model the environment. And POMDP, I mean, partially observable Markov decision process is like at any state, if you're going to take an action, you'll not be able to fully observe the outcome or the next step. So somehow you have to deduce it. So you can probably, let's say you're traveling through a maze, and so that maze is not properly lighted. Okay, there are a lot of dark places. Now, when you start traversing the maze, you're not able to see the whole state space. Okay. Probably when you just take an action, after taking action, you will just get to see the next observation, and not more than that. Okay. So that's a example of form defeat. So of course, like partially observable environments are very difficult to solve because the state space is not known beforehand. Okay. So planning is hard. Rather, it is NP hard. So planning problem, even if all the state space is known, it's very difficult to solve. I mean, so there is a a term called NP hard, NP complete. Okay. So NP hard means so we are basically the computer scientists classify certain problems in certain classes. Okay. Some class is called the P class. That's the polynomial class. That means for those problems, um, the problems can be solved in a polynomial time. And then comes the NP class. So in this class, the problems can be solved in a polynomial time or cannot be. Okay. I mean, for a non-deterministic machine, it can be solved in a polynomial time. So in simple terms, if you use our traditional computer, it's going to take maybe, let's say, exponential time to solve it. Okay. But those problems are verifiable in a polynomial time. Now, then comes the NP hard. So NP hard is the hardest of all problems. Okay. So in simple terms, it means like it is unlikely that any polynomial time algorithms exist for NP hard problems. Okay. And if we find some like fast running algorithm which solves the NP hard problem, that means we could solve any problem in the NP class. Okay. So there are a lot of different difficult problems in the NP class. Uh, the gene editing problems, the cancer problem. So if you are able to find any one solution for any one of the NPR problems, you'll be able to solve all the problems in NP class.
By the way,
But of
just
course,
on this point on planning, like
yeah,
by searching over the solution, I mean, I can treat it as some form of like finding the shortest path from node A to node B, right? Like pathfinding. Is that considered
yeah,
planning as well in the terminology you're using?
yeah. Like if you consider like finding the shortest path from one path to another, so that's planning along with optimization. Okay. So see, like if you try to find out a path towards a goal state, it can be optimal or it can be a non-optimal, it is a suboptimal path. Okay. But if you want to find out the shortest path, it should be an optimal path. Okay. So along with planning, you are also doing optimization. So of course, like both of the terms go hand in hand, and planning with optimization, of course, it's a NP hard problem.
Okay, so this is
Yeah,
can I draw something on using the annotation? No,
yeah.
I'll just draw some notes here because I think this is a very interesting point. You said planning is hard to find, like intractable. So let's suppose that I just draw a shortest path finding. Okay, so in reality, it need not be shortest path. It could also be like what sequence of actions from a start state to a goal state, right? So essentially, you could represent like states and actions as a graph like that. So the circles
Yeah.
are your states, and the arrows are your actions. So like this is exactly like what you would say as a Markov decision process if your if your arrows only linked out from one node like that, independent of the earlier nodes. As long as I know this circle here, I can go to the next node. Yeah, but like partially observable will be like you don't know what came before, you could be in any state that looks similar. Yeah. So let's not go into there. We just talk about Markov decision process. I just want to ask, could you go back to your previous slide?
Yeah.
So you said that it's very hard to find a planning problem. Like it's NP hard to get the solution. So does that like apply for like graphs that are infinite, or even for finite graphs? Like that means that there's only a fixed number of nodes here. Because like you
Yeah,
could probably do a brute force search over finite nodes. So use this statement that you are making, is it for graphs that have infinite nodes?
no, this is true for the finite node graphs also. Because maybe I'll just show one. This is one diagram for planning. Okay, so understanding this diagram will make it clear like how this planning problem is, uh, you know, uh, difficult to solve. I mean, it requires kind of an exponential time if you do a brute force search. Okay, the one that you drawn, it's like these nodes are states. Okay, so I have represented the whole planning search problem as a tree search. Okay. But of course, like you can also represent it in the form of graph where similar states will be represented by a single node, okay, the one that you have just drawn. Now let's say there are multiple actions. Let's say in this ScienceWorld environment, you are at a certain space. So that is one state. You are at the hallway. Okay, that's the root state. Now you can take multiple actions. Like you can open the door to kitchen, open door to living room, look at the picture, look at the air. There can be multiple different actions. Okay. So once you take those actions, it's going to go to the next step. I mean, if you open the door to the kitchen, the door of the kitchen will be open. Open the door to living room, door to the living room will open. Now, once you go to this next step, there again can be multiple different set of actions. Okay. So this tree is going to grow. Okay, this thing is going to grow exponentially. Now, if you need to find a sequence of actions that's going to take you to a goal state, and if you're trying to do a brute force search to find the solution, then it's going to be exponential space. Okay. Of course, you cannot solve it in a polynomial time. So even if there are finite number of states or finite number of nodes, still the solution size increases exponentially with the number of nodes.
Yeah, I
So
understand
that's
this
the
now. So basically it's something like, although it's a fixed number of states, if your fixed number is so huge, whatever search algorithm you have will actually have difficulty as well if you just do brute force, because it might take too long. Like for example, the game of Go or game of chess, if you want to simulate all moves, you might wait until the universe ends before you can compute the answer. So I think something
yeah.
like this is what you are talking about, like that planning is a tough problem, is NP hard. But there's something I would like to like highlight here. You also mentioned that once you found the solution, checking it is easy.
No, that is for the NP problems. But NP hard problems, the verification is also, exponential in time for NP hard problem. But if those are NP complete problems, that means, so maybe I'll draw something. So this is the, okay, this is the NP class. Now allow, so there is a class outer this region. So this is the NP hard class. Okay, make it as 8. Now this is a whole set. Now this intersection of NP hard and NP class, so this is called the NP complete. Okay. And within NP, so there is another subsection. This is called the polynomial, like the T class. Okay. Now NP complete. So actual planning is a NP complete problem. Okay. NP complete is basically the intersection of NP hard and NP class. Okay. So that means for the NP complete problem, the criteria for finding a verifiable like once you give a solution, the time to take to verify the solution, uh, it's going to be exponential. That criteria is not applicable for the NP complete problem. So that is a strict criteria for the NP hard problem. So for the planning problem, so there is no restriction that the verification once a plan is generated, the verification is also going to take exponential time. So that's not a restriction imposed on planning problems. Okay. So probably I can give one example, like say chess. Okay. So chess, like if you are given a specific solution, So the verification also takes exponential time. Okay. Because if that solution is going to work, you have to play it along, okay, along with the opposition. So that is purely NP-hard problem, and it's outside this set. But planning is an NP-complete problem. Okay, so the verification might take exponential time or might not take exponential time, based depending on the problem set.
Got it. Thanks
Yeah.
for entertaining questions. Actually, I asked all these questions because I wanted to just bring about a food of thought here, which I'm going to say right now, is that, our brains do some planning, but I don't think it's doing planning in the form of these algorithms where it seeks to find the optimal plan. Okay, because if,
Okay.
if that were the case, we would be taking too long to get a plan out. Like, I mean, a lot of things are MP hard in real life as well. In fact, a lot of partially observable as well. So the way we are doing planning might be something to do with more of a pattern matching to match a plan. Or I mean, at most we simulate like 2 or 3 depths. Like
Yeah.
with that, we can survive in the world. So that's just food for thought. So I leave you to continue the rest of the presentation because I don't want to disrupt the flow. But yeah, just think about it, like how are we like seemingly able to solve such a hard problem, which is to plan like even for finite states, but a lot of states. Like the human brain is able to do that. So let's just think through that as we continue the presentation then. Yeah, Sona, please.
Yeah, of course. Like, see, if it is an NP-hard problem, then it's very difficult to solve. I mean, using a traditional computer systems, then of course we have to find out some alternative way or use some kind of heuristics. Okay. So by using some heuristics or pattern matching, probably we cannot guarantee like it will always find the optimal solution, but it will give you a workable solution. So that's what we want. So if you can search through like finite number of depths in the tree or use some heuristics or do some pattern matching, it will give you some workable solution. That's what all we are doing in the computer science domain. So we are not trying to find out the perfect solutions for NPR problem because till now we don't know like if there is any perfect solution for NPR problems. If we know, then probably NP equals to P. So that's a very open question. Okay. Okay, so this is the environment. Sorry, how do I move this drawing? Do you know, John? Okay,
Yeah,
good.
I'll help you remove it.
Yeah, yeah. So this is the environment that I'll be using to demonstrate, how our designed agent is going to work. So it's basically a game playing environment. So it was designed by Illinois Institute. Uh, so So this environment contains like hallway, a workshop, art room, a living room, a kitchen, bathroom, bedroom. Okay. So this is the agent. So the agent can go to different parts of the environment, the workshop, art room, living room, greenhouse, and there are multiple objects in different rooms with which the agent can interact. So there is a stove, freezer, uh, a glass, water, and a lot of other different things. Now, agent is given a specific goal. Let's say one goal is like to boil a water or to boil any substance. Okay. Then the agent has to find the water, maybe pour the water in a certain container and put it on the stove and then turn it on and then boil it. Okay. So in this way, like the agent are given multiple different tasks, mostly a kind of a very simple scientific task. And it is expected the agent will be able to carry out or complete the task in the environment. Now, this is a very difficult like environment. There are a lot of different objects in the environment to interact with. So, of course, the state space is huge. Along with that, the agent can take a lot of different actions. Okay. Uh, the agent can open the door. It can pick up some object. It can pour some object into another container. It can turn the stove and a lot of different things that agent can do. And the number of actions is not fixed. I mean, let's say the number of actions that the agent can do within the hallway is different from the actions that it can do in the kitchen. Okay, because the number of objects in the kitchen are different and the number of objects in the hallway are different. And also this environment is partially observable. Like initially the whole environment is not known. the agent can see only its immediate, environment, the surroundings of it. And once the agent goes to a different room, let's say it goes to a kitchen, then it can observe what's there in the kitchen. So at the beginning, it doesn't know like what the environment is all about. So in this, all these things makes this environment very challenging to solve. Okay. So this one I was explaining like why planning problem is very hard. Like uh, this is due to the exponential nature of the uh, exploration that is needed to solve a planning problem. Now there are a lot of different work addressing the planning problems. I mean, state space search is one of the major area which scientists has worked uh, and used the state space search to solve different planning problems. But there are certain problems with state space search also. So the first problem is the combinatorial explosion on the state space side. So if you see in this tree, so as the number of state space increases, so you can imagine this tree will expand exponentially. The number of nodes will expand exponentially. Even if you represent it in the form of graph, it will also like expand. The search space will actually expand exponentially. So that's the major problem for like the combinatorial explosion with the state space site. So some of the old algorithms for doing state space search is depth first search, breadth first search, is A star search. So depth first search is like representing the search space as a tree, and it's going to search towards in one specific line, and it's going to full depth. It's going to go to the full depth before reaching to the end state, and then it's going to go and search in the next line. So depth first search, you can imagine if the state space is high, it's going to go on digging through the depth, and it's going to take a lot of time. Breadth first search is like it's going to search in a horizontal manner. Okay. So it's going to search through all sibling states, and once all states in a specific level is completed, it's going to go to the next level. So here also, let's say if the action space is very large, okay, like if you move to a specific state and there are say like 10,000 actions you can do, then you have to expand 10,000 nodes. Okay, so that's also going to be very problematic. A star search is also state space search, but it's going to take a help of a heuristic. I mean, like it's going to estimate the cost like from traveling to the root state to the current state, and then it's going to estimate like what will be the cost from traveling from the current state to the goal state. So using those estimates, like it's going to plan out the most probable path in the state space. So that's going to reduce the state space a little bit. I mean, the search space a little bit, but still, uh, uh, if the state space is high, action space is very high, it still is going to take a lot of computational resources. The next problem is like some heuristic based algorithms. Heuristic means like we need to come up with some estimates about the cost, or maybe some hints what should be the probable path to reach the goal from the current state. Okay. So this constructing the heuristics might be a problematic thing, because it needs a lot of prior knowledge about the environment. So let's say if you consider the A-star search, for every state it needs like what will be the cost from the current state, what is the cost for traveling from the current state to the goal state. So that estimate is needed. So in order to calculate that estimate, a lot of knowledge about the environment is needed. So we need to have a number that is denoting uh, the cost between every pair of states within the environment. Otherwise, we will not be able to calculate accurately like what will be the cost from traveling from current state to the goal state. So other algorithms are like hill climbing, and T-star is like a modification of A-star used in robotics path planning. So hill climbing also, it's like optimizing algorithm, like it's going to reduce the error or a distance to the goal little bit by bit. Okay. The same problem exists for all of them. And even for the sampling based algorithms, in many cases, like we need a lot of samples when the action space is large. So sampling based algorithms are like MCPS. Okay, so that's a very popular one, Monte Carlo research, where basically when we don't know the environment beforehand, like we don't know the full state space. In that case, like we have to explore the environment and find out what are the available states in the environment. Okay. Based on that, like we can use some measure or some heuristics to explore a certain part of the tree or certain part of the state space to guide the search. But even to come up with a good measure or a good exploitation strategy, we need to have a very large number of samples drawn out from the environment. Let's say in the MCTS, like in the Monte Carlo research, what happens, like you go to a state, okay, and there are certain child states attached to it. Okay. Now you have to select which child state you are going to explore. So there is a certain measure, the value matrix. So using that, you are going to select a specific child state. Now it goes on selecting those child states and it comes up with a specific path. Now, let's say it goes to a leaf node. So in a leaf node, so there are no child states. So nothing has been explored so far. Now you have to, you have to do some exploration. So in that case, a random exploration is applied. Now let's say there are 10,000 actions. So out of 10,000 actions, you have to choose randomly a specific action. Okay. So in this way, like if the action space is very huge, a random exploration, if you are going to do a random exploration, of course, like you have to draw a lot of samples out. Otherwise, you will not get an idea of how the state space works in that region. So that's the problem with sampling based algorithms.
Thanks, Swarna. Anyway, in the interest of time, maybe we don't need to focus too much on prior work. We can just go straight to your algorithm. Yep, so that we can discuss more.
Yeah. That's what I was thinking. Right. Yeah. So maybe I'll just briefly give what are the problems of RL. Like problems of RL is like this also did a lot of trajectories of samples to learn, and it performs miserably if there is fast rewards. I mean, the rewards are very less. Like rewards are basically the feedbacks based on which the RL algorithms adjust itself. So if you don't get feedback, there is nothing to adjust. Now the problem with LLM. So LLMs are mostly like if you do planning with LLMs, those are mostly shallow in nature. So they mostly do greedy pattern matching and no logical constructs within it. Now, without memory, if you're trying to do a multi-step reasoning, so of course there is a limit. Like it has been like experimented. Like LLMs are not very good at multi-step reasoning. So at most, like in the worst case, it will be limited by the context window size because you have to provide the knowledge about the environment to do a multi-step reasoning. So if you are doing a chain of thoughts planning, then like the multi-step reasoning is limited by the context window size. And next thing is like it tends to overfit quickly and getting stuck to a local goal. So there is one example, like while solving this like ScienceWorld environment, so there is a boil task, like you have to boil a specific liquid. Now there is another subtask within this environment, like you have to focus on certain objects. Okay, so focus is like a specific action. So focusing on wrong objects causes environment to reset. So that is one learning or a belief that is captured while exploring the environment. So once this specific learning is captured in the memory, in the subsequent steps, the LLM tries to find out the right object to focus instead of finding the water source. So in this way, like it got stuck in finding the right object to focus instead of solving the actual goal. The next problem is like lack of exploration. So this is another example that I've taken from another paper called Clean. So they are also they have also tried to solve the same ScienceWorld environment. So there is a task of creating an orange pen. The agent is supposed to find red and yellow pen in the art studio, and they mix it and build the orange pen. However, initially the art studio is not visible from the hallway. So unless the agent knows like the paints are available in the art studio, so it tries very alternative method. I mean, very local methods. I mean, it takes some irrelevant objects and try to mix them and builds the orange paint. So this is another problem.
Actually, this slide is very important. I actually agree with all these points. Like the main one, the one that you mentioned, the second one, tends to overfit to your prompt. Like the way you prompt matters a lot. Change the prompt, change a little bit of the wording, like from find to search, you might get different behavior already. It's all because of the pattern matching ability. Similar to point one, which is like the pattern matching and not doing logical thinking. The last point on exploration is also very realistic. Like based on pattern matching, you only get certain outputs, right? So you may not be like Monte Carlo tree search where you randomly explore another branch. Like based on the context itself, you get fixated to only a certain set of actions. So I mean, I do have some ideas on how to solve those, like maybe multiple agents with different biases, different contexts, and imbuing some form of logical planning to check the LLM's outputs. So that's LM modulo. I mean that series of methods.
Yeah.
So yeah,
Yeah.
I think this is a promising direction with LM guided search, but the problems here are real, and yeah, let's see how you address them.
Yeah. Yeah. Okay. So this is the strategy that I've taken to solve it. I mean, the state space search, combining state space search with RL, with LLM, and with reflection. Okay. So the idea is to do a state space search based on whatever is known at any time, balancing exploration and exploitation. It's similar to MCTS. Like uh, the whole state space is initially not known. So we are going to explore the state space, and whatever is known at a particular point of time, we are going to store it in a memory as a state space graph. And in future episodes, probably we'll exploit the state space graph to find out the initial set of actions. And whatever is not known, probably we'll use the LLM to guide our search. And these purely LLM based approaches, they mostly ignores the rewards that are given by the environments. Now, if you're getting some rewards, probably it's a sparse reward. But if you get some reward, let's use it. Okay. So the idea is to if you're getting some reward, we'll be using it to update the state space graph, so that in future search, the value matrices are updated, and it will help us to better guide the search and better exploit the state space graph. And as I said, where random sampling is needed, like if MCTS, if you go to a leaf node, or if you go to a node where random exploration is needed, so we are using the LLM to focus on selecting samples, because the LLM has better knowledge about the world, so it has the initial bias, and it will help us selecting better set of samples, better set of action sequences where random sampling is needed, and that's going to reduce the search space to a great extent. Next is using reflection strategy to enhance the sample selections. I mean, reflection is whenever you are exploring the state space, you're getting some observation from the state space, and based on the observations, certain set of learnings, certain set of summarized learnings are being captured, and those are being stored in a separate memory, and those learnings about the environment are again put into the prompt, and that's going to help us guide the search in a better way for future queries to the LLM. So this graph basically denotes the state space search graph that I have used. So this S0, S1, S2, these are the state spaces, and A1, A2, A3, these are the actions. So let's say the agent starts with an initial state called S0. Now it took an action A1, it goes to S1. If it take action A2, it goes to S2. In similar way, during exploration, these type of state space graphs are getting constructed. Now, let's say while like solving a specific problem or like while going towards a specific goal, let's say S10, the agent has to travel from S0 to S2 and then to S3. And after S3, so it's a leaf node, there are no nodes available. Now here a random exploration is needed. So here we are like querying the LLM with a specific prompt, like with a specific knowledge about the environment. I mean, the learnings, the current state space description, the action set, and all those things. And we are asking the LLM to generate the best probable set of actions that's going to take the agent to the goal state. Now the LLM comes up with a set of actions. That actions may not be a perfect one, but we are going to execute those actions in the environment and record the outcomes. Okay. And based on the outcomes, we are again going to modify the state space graph. And in the next episode, we are going to utilize the the state space graph that has been constructed, and we are going to find out the rest of the solutions where the state space is not known using the LLM.
Oh, okay. Can I summarize my understanding of this graph to see whether it's correct?
Yeah.
Let me try. So basically, this part here is whatever you have experienced before, right? Like in the last few episodes transition, you realize, oh, I start from here, I took this action, I reach here in real life. Then I record this in some knowledge bank, which is like the state space tree here. Then basically do you use some form of, I think you go through the equation later, but use some form of Monte Carlo tree search exploit, right? To select which node to go down based on some value and whether it's explored before. And then once you reach a leaf node, then you expand it. And basically this expansion in Monte Carlo tree search is usually random selection or selection based on the policy. You are using the LM as like the policy to explore. Use LM as the policy from leaf node to explore all the way to goal state if it can be reached.
Exactly. That's right.
What if you can't
That's
reach
right.
the goal state then? Then how do you terminate your LM?
Yeah. So the LLM is going to give out some plan, a finite set of action sequence. So of course, like it might not get to the goal state. So those action sequence will be executed in the environment, and the outputs will be recorded. Okay. So those will be the action observation pair, and those observation will be encoded into a specific step. And again, those action and state sequence will be used to update the state space graph. So after
Oh,
S1, we'll be getting another set of action state sequence. Okay. Those action state sequence will be used to update the state space graph. And since this is a graph and not a tree, so there can be an overlap. Let's say the LLM takes a specific action, A3. Okay. Now A3 goes to S3. And after S3, it then takes another action, say A5. It goes to another state, say S10. In this way, the output, the sequence, I mean the trajectory will be updated in the state space graph. The logic is like if a specific state space within the trajectory, I mean the specific state within the trajectory is not present in the graph, a new node will be created. Okay. If a specific node is already present in the graph, but no age is there, so age represents a specific action, then an age will be created. Okay, representing that specific action.
very nice. Do you only create the immediate action and state, or you create the state space graph for all the actions and states that this exploration plan has encountered?
It's going to create all nodes in the trajectory. I mean, in the whole sequence.
Nice. So if let's say I were to draw this, let's say this state leads to like an action A7, and then it goes to state 3, or maybe state 5, and then this state 5 maybe it takes another action and goes to state 0.
Yeah.
So you will record all this, and then it might link back to the graph again, then it might get another action, like maybe you can take action A1 again and go somewhere else. Like you can take action A1 and get to another state here. So you record all this in your graph, is it?
Yes.
How do
So
you
let's say,
determine when to stop? Because it can last like quite forever. Or is there like max number of actions that you can take in the environment
yeah.
before the
So the
environment
LLM,
ends?
Yeah, so the LLM basically, so what I'm doing is like, so we are prompting the LLM to generate a sequence of action at one go, one single query. So the LLM is always going to return a finite set of actions. Okay. So it's not going to loop forever. So let's say it's going to return a 10 set of actions. So there will be at most 10 iterations within this state space graph. Okay. So from S1 it goes to S5, then to S0, then to S2 probably, and then to some other state. In this way, it goes to 10 different states. And once we record all the different transitions, so we stop. So the trajectory is always limited. I mean, always finite.
Very nice. I like how you are incorporating all the experiences they are gaining and inputting them into your knowledge. I think that's very useful because then you can learn from as little experience as possible. One final question before you move on. This part here that I highlighted in blue, will this ever happen that based on a certain state S0, you take action A1 and you get to two different states? Will this ever happen in the state space graph, or is always like from a certain state you take a certain action, you always get back the same output state?
No, in this environment is basically deterministic environment. Like if you take a specific action, it's going to take you to only one single state. Okay. That's
All
how
right.
like I encoded it.
Are you going to
But
explain how you come up with the states? Because I'm interested to find out like how you define this state to ensure that, when given this particular state and a certain action, you always reach another state. Like how do you define this state? Are you going to cover that later?
yeah, basically maybe I'll show you one example. So it's very simple. Like I haven't used any special strategy, but yeah, there are scope of improvements on encoding the state information. So what I'm doing is like just taking the observations. Okay. So the observations returned by this environment is in a natural language. Okay. So let's say the agent is in hallway. So the agent, it says like this, the agent is in hallway. It sees a ear, a picture, certain walls, certain doors to kitchen, a door to kitchen, a door to living room. This way, like it explains the whole observation in natural language. And there is another part of the observation, like which is basically called inventory. So if the agent has picked up something, let's say orange, then the orange is in the agent's inventory. So if you query the inventory within the environment, so it will return. So there is one orange in the inventory. So I've used both these things, the raw observation and the inventory observation, and combined them. And that whole natural language statement is a state. So that's a very crude way of doing the state, but at least it worked for this one. But of course, like encoding the state information, like there are some scope of improvements. Probably we can apply some kind of embeddings, so that related states become closer to each other. So those kind of strategy we can apply in future work.
I understand. So basically, you give all the metadata that the agent has, inventory, location, those things that would be invariant. So given everything that you gave in the state, you don't need to know the past actions. You could just based on their state and come out with a decision. Like everything you need to know is inside the state
Yeah,
itself.
yeah, exactly. Yeah. So it's converting. It's a basically a Markov decision process.
Yeah, I like it because actually the Markov decision process much easier to navigate than the partially observable one. Like the
Yeah,
partially
yeah, yeah.
observable, yeah, is a pain to do it. Okay, yeah,
Right.
I don't want to disrupt too much of it, but thanks. I like this idea of updating every single transition you have experienced and, getting the state space as a source of ground truth to like project your planning further so that you don't have to plan all the way from the start. You can just go to some intermediate node based on your exploit condition, and you can
Yeah,
then explore from that leaf node. That is great because you are getting closer and closer to the goal state as you use this method
exactly,
of
exactly.
speech.
Yeah, yeah,
One other question. Sorry, I had another question now.
yeah.
Uh, what if the state transition is different from your graph? Let's say, for example, the environment change. From state 0, I take A1 now, and instead of going to S1, I actually go to S7 instead. Then how would you update your graph in this case? I don't know whether science will have this changing environment, but in real life there is. Like you do a certain action, like pick up your phone, you might get different messages every time. Yep. So how do you change? Like, how do you decide whether to change this earlier part of the state space graph?
Yeah. So basically, see what I did. So here the state information is encoded in such a way. Uh, let's say a glass of water. It's there in the kitchen. Okay. Now you did some action, and the glass of water, you took the glass of water, and you kept it in a living room. Okay. So the environment got changed, but the the agent has changed the environment. So there is no external agent which is going to change the environment. So in this case, if you take the glass from the kitchen to living room, so the state also got changed. So it will be a separate node in the state space graph.
Okay, I understand. So in the science world environment, basically this dynamic world changes don't really occur. So you don't have this issue where you have
Yeah,
conflicting information as to what you can observe in the real world and what you saw in this state graph. That's correct?
exactly.
Yeah. So
So
I think
let's say
this part, is it implemented? I mean, the memory forgetting part, or it's not implemented for this work?
no. Memory forgetting part, it's not yet implemented. So the one that you said, like if it is a dynamic environment, like where some external agent or some different forces are going to change the environment. So there, what we can do, like see, if the environment gets changed, then the learning part, like adding the nodes, it's going to work. Like if you are going to encounter a new step, we are going to add a new node or a new edge. Okay, but let's say a previous transition, a state transition, is invalid at this point. So in that case, like you have to employ some kind of forgetting or some kind of deletion of edge, or maybe a deletion of node. So that part is not yet employed in this state space graph, but probably, yeah, we can think about some strategy to
Yeah,
employ.
maybe like if you see the same thing 3 times, then you delete the first observation, something like that. Yeah, some forgetting rule might be useful
Yeah,
to help it to learn new stuff. Yeah. Anyway, this
yeah,
is
right.
my interest because I want to make agents learn in dynamic environments. So I do think this has some promise, and yeah, I leave you for the rest of the presentation then. If
Yeah,
not, I'll be
yeah,
asking all the way. Yeah.
yeah, no problem. Okay. So as you have guessed, like the state space plan selection, like in the graph, like uh, we need to have some kind of measure to select the next state from a specific state. Like each action needs to be selected, so there has to be some decision. So it's basically the same upper confidence bound interval like that's used in multiple lot research. Like we are going to assign a value for each of the different states. The value is based on the rewards that are getting, like that we are going to capture after taking different actions. So along with this value, a certain exploration term is added. So log of suitable log of n by ns. So log of n is basically the total number of explorations. I mean, the total number of state-based visit that has been done to all the parent nodes of a specific state. Okay. Now here, like it's little bit different from the Monte Carlo tree size because that was a tree and there is a graph, and a specific node can have multiple different parents. In a tree, like a specific node has only one parent. So here the capital N denotes the sum of all the visits for all the parents for a specific node S. And ns, the small ns, is the number of visits for a specific state S. So in this way, if a specific state is visited less number of times based on the number of visits of all its parent nodes, so this exploration term will increase and it will, drive the search towards that specific state which has been explored less. And this is the logic. Like we are just going to select the next child state or the action for which this v plus s is maximum. And this continues like until a leaf node is reached, or the maximum v plus, I mean this whole value, is less than the default exploration, or a closed loop is selected. So default exploration I'll come in the next slides. So let's say you come to a specific node uh, where there are certain child nodes. I mean 3-4 child nodes are there, but that specific node is not fully expanded. Like all the child nodes are not explored. Now, if you just continue exploiting the the 2-3 child nodes will not be able to explore the rest of the actions that are possible from that specific step. So that's why so I have assigned a default exploration factor. So based on this default exploration factor, we are going to decide whether from a specific state we are going to move to the existing child states, or we are going to explore new states from the specific node. Okay. So state space exploration, I've already explained. Like so, this V plus captures both the matrices of exploitation and exploration. So as I explained, like this will work only for the visited nodes or the visited states. So whatever states in the graph is known, so we can calculate this matrices for them and we can exploit them. And if some states is unexplored, then we don't know about any, we don't know anything about them. Okay. So there needs to be some way to explore the unexplored states. Simple random exploration, like in MCTS, it becomes quickly untrackable, like if the action space is very high. Now, deciding on the exploration, as I said, like there is another term called V explode, okay, that is assigned, that is calculated for each individual nodes. So V explode is basically a sum of V default and a specific term. Okay. So V default is a very constant value assigned to every node. Let's say it's a 0.5. And Ks is basically a factor. And C is a constant. And this is log of the number of visits of that specific state. Now Ks is basically this metric. So As minus As bar by As to the power n. So As is the number of actions possible from that specific state. Let's say you are in a specific state and there are 1,000 actions possible. So As will be 1,000. And As bar is the number of actions already tried from that state. Let's say you have already tried like 100 actions on that state. So there are 100 child nodes. So this As bar will be 100. So we are actually subtracting the number of child node, the number of actions which are already tried from the total number of actions. So this will help. So this is basically an exploration term. So we want the exploration term to be high when the number of actions, number of untried actions is very high. Okay. So there are a lot of untried actions. Then we want to explore those untried actions. Now, if the number of untried actions becomes less, so once we keep trying different actions, then this factor, the Ks, will reduce to 0. Okay. So whenever all the actions are tried, this Ks will be 0. Because in that time, we don't need any exploration from that state. All the states are known. So that's what about the V exploration factor. Now, this Vk is dash. So this is basically, in other terms, we can say the Q value of a particular state S. So Vk is dash is basically, so S dash is a child state of a specific state S. Okay. So Vs dash is the value of the child state S dash, and this is the exploration factor, this one. Exploration factor multiplied by this Ks term. Now, you can also convert, you can also like consider this as the Q value of the state S. So it basically specifies, like if we take a specific action from a state, like whatever it's known, okay, with respect to the maximum Q value, if that is going to give more reward, or mean it's going to take us to the goal state with more guarantee, or like exploration will be more beneficial for finding the goal. So this decision we are going to take by comparing these two matrices. Okay. So if V explode is greater than this VKS dash, then the subsequent action plan is generated using the LLM. I mean, exploration is needed.
I'm just curious, is this a well-known equation or you came out of it for this case?
This is not quite a well-known equation, so we just came out of it.
Yeah,
So Q value, like we already know, but I have just modified these matrices, like adding this case term and all those things there.
Yeah, in traditional Monte Carlo tree search, you actually do some form of exploit for each action. So that means that if this action one, A1, let's say this is state 0, and this goes to state 1 with A1, and then you actually have A2 over here, which is untried. Okay, but you have a exploration term to bias it to try that, and you have a A3 here, or I mean as many actions as you can. There's untried,
Yeah,
and all these
yeah,
are biased using the exploration term, which is like you have your okay. Let's say you have your okay. You use V, right? So let's say you have your V state prime plus the exploration constant C square root of ln n over ns
yeah.
over ns prime. Yep. So wouldn't this already be able to bias the exploration to the unexplored nodes? Like, because as long as you have a way to characterize what are your actions, I'm assuming in the environment the actions are finite, right?
Yeah, but this VS prime, you can only calculate for the known states. Let's say you are at state S. So S prime are the child states of S. Okay. Now, if you are going to select in any of the child states S prime, so you can take a decision based on the value of the, I mean, the V plus of those child states. Okay. So you can select the maximum, uh, uh, V plus for the child state, like, but
Yeah,
if
no,
we
but
don't know the child state,
the thing is for Monte Carlo tree search, even if I don't know the value of this like action 2, because I don't know this state, I can just simply treat this value as a 0 because it's unexplored, or like you can treat it as a base term. Sooner or later, this term here would increase high enough such that you would choose this branch over this original branch. Like because of the exploration term, you would increase as you don't explore that, right? Like I'm just thinking, why can't you just use the original Monte Carlo tree search equation to decide whether to explore a different branch?
yeah, this one, see, this one is going to be high, but how do you know, like, you're going to do a random exploration in that during the expansion?
Oh, normally the expansion step you expand one node, and then from that one node you do your policy or random exploration. So this is
Yeah,
the next node selection, which is based on this upper confidence bounds this equation here.
yeah, yeah. So basically, like, if there are multiple, child states already there, like S1, S2, S3 in the state space graph, then you can use this equation to decide like which child state to select. Okay. But let's say certain actions are there which are not explored yet. So in that case, like, how do you select, like, whether to do a random exploration or select the child nodes like which are already there in the state space graph? So in
Oh, so
MCTS, like,
you are talking about bypassing the child node and doing another exploration, is it? Like
yeah,
basically
yeah, yeah,
instead
yeah.
of going to this value here, I recalculate the value somewhere else.
Exactly, exactly. So
Oh,
this
but
VH
why,
flow class,
why would you need to do that if your child node is always going to be the same, right? Like it will always go to S1 when you take action 1, right? You won't have a case where you go action state 2 when you take action 1.
no. Let's say there is a parent node S. Okay. So from the parent node S, so there can be, let's say, multiple, like 10 states, S1 to S10. Okay. So 10 different actions take from S to S1 to S10. Now, let's say till now we have only explored like S1 to S3. So 3 states are known. So for these 3 states, 3 child states, you know this VK plus. Okay. Now you can calculate this metric for these 3 states, S1 to S3. And based on this metric, you can select which child state to explore, like whether S1, S2, or S3. Like you're going to select the maximum of these 3 child states. Now, there are other child states like S4 to S10. So those are not yet explored, like those are not yet in the state space graph. So you have to have some way to explore those states. So for them, like, I'm like calculating a default V explore plus and assigning this value to all those unexplored nodes like S4 to S10. Okay. So in MCTS, what they do is like if some specific node is not fully explored, so they are going to explore, do the random exploration. Okay. So they're always going to do random exploration if that specific node is not fully expanded.
Okay, I get you. So basically for those nodes labeled here like under A2 and A3 in my graph, you use this vExplore plus term to decide whether to explore them. And for nodes that you have already explored, you use this VK plus.
Yeah, yeah, right.
Yeah, the what I'm saying is that I think your VK plus can also be used for the unexplored nodes. Like all you need to do is use the same equation for them.
Yeah, but for the unexplored nodes, like how do you get the VS prime?
Yeah, just put zero. Just put zero.
Yeah, in the instead of zero, I just put a V default.
Or you can just
I
put V
mean, it's a
default for this
constant.
also. Yeah.
Yeah,
No, bro. I
it's
mean,
a constant value.
if you look at the equations for VK plus and vExplore plus, it's actually
Yeah,
about the same, right? I mean, if you think about it, what's the difference between this term and this term here? Like, it's only the factor here, right? Which means that you can just also increase this exploration constant here, and these two equations would be similar. I mean, barring the fact this V default can be the default value of this. So actually, these two equations can be the same equation if you think about
yeah.
it.
Actually, these two equations are same. In fact, these two equations are same. The only difference is like the V default is a constant here. So V default because we don't know the value of a unexplored state. So VS prime is being updated after every run using a temporal difference learning. But V default we don't know for unexplored state. So for this
Okay.
unexplored state, the V default is 0 or maybe 0.5 or something else. Okay.
I got it. So you want to just give a default value for unexplored nodes. I think
Yeah.
essentially what you're saying is that you give some optimism so that you explore some of the other unexplored states sometimes
Yeah. Yeah.
rather than just going through the known path. So anyway, how you do the explore in Monte Carlo, I think it's not too crucial. The main thing is you explore all nodes eventually. Like
Yeah.
so you can use this equation, but I'm just saying that the default Monte Carlo tree search would probably already suffice for your use case. I mean I don't think you need an additional V explore, but I mean this is just some I mean insights I have. I mean I look at your equations, I don't see much difference also. So unless there's some experimental value to it, like you have tried the default one and it didn't work, then this V explore works. Then I'm interested to know. But otherwise, if it's just like a heuristic that you have come up with that is not really tested empirically, but it just works, then I think we can move on because I mean there are many ways to implement this.
Yeah. It's like a basically heuristic, but as you said, like there's the equation is not much different. Structurally, you can say it's same. Only difference is like as I said, the V default is a constant here, and say S prime is a changing one. Yeah. And this KS term that I've added, so KS is basically used to control the exploration term based on the number of actions that it has already explored. So that's a new addition. It's not all there in the original UCB, the upper confidence bound.
Yep, nice,
Okay.
cool. I mean, I think this is fine. The main thing is we explore and exploit. And we even explore unexplored nodes. That's the main takeaway.
Yeah.
Yep. Okay.
Yeah. Yeah. Okay. So once an action plan is generated, so it's executed in the environment. As I said, like for each action, the observation is recorded and it's converted to action observation sequence. And the reward is also recorded from the environment whenever it gets some. And yeah, the total number of actions available in a certain state, so that is also recorded because that is used to decide, calculate that KS term. So all these informations we are getting from the environment, the ScienceWorld environment. Now, state space learning, like how does it happen? Like so in action, so basically, as I said, like we are converting the observations and inventory and clubbing them into a state. Now we are getting an action state sequence. So every action state sequence have a start state and an end state. So those whole trajectory is being mapped into the state space graph. So the logic is like this: if both the start state, so let's say there are 10 different states in the trajectory. Okay, S1 to S10. Now we'll take the first two states, S1 to S2, and S1 will be one node in the state space graph. S2 will be another node in this state space graph. So if both the nodes exist in the graph and no edge exists between them, then an edge will be added. The edge represents the action. Now let's say S2 is not there, the node is not there in the state space graph. So a new node called S2 will be added in the graph. And let's say both the nodes exist and also the edge exists. In that case, the visit count will be incremented, the number of times it has visited. And let's say like if a specific action is taken and after taking that action, it goes to a say invalid state. Okay, so it's an invalid action. So some failure has happened. So there is a certain invalid node. It's a constant node. Then the edge from that particular state goes to that invalid node. Now, once the state space graph is updated based on the trajectory, the value of all the nodes are getting updated by a temporal difference learning. So this is a very common learning method, and this is a well-known equation for like doing a error-based learning. Whenever the full state space is not known, and we are iteratively like updating the values for different nodes.
Over here, the reward R comes from the environment, right? Like, so is it a sparse or dense reward situation that that the science world is?
So ScienceWorld, it's basically a sparse reward. Like if every action, after every action, we are not getting a reward. Okay. And in some environments, it's very sparse. Like we have to take a lot of actions after which we are going to get some reward. But once we get a reward, the reward value is very high. So if you get a certain reward, then the update, the value update in the state space graph gets quickly biased to a specific nodes. But yeah, if we don't get rewards frequently, so unless we don't get any reward or feedback from the environment, so it's basically a difficult search.
I understand. So once you get the reward, basically you can prioritize the set of actions that led to the reward very fast because you do this temporal difference learning. And you can bias your state space search along the path to the reward. Okay, Ken, thanks.
Exactly. Right. Okay, so this is the agent architecture. So here we have the state space graph where all the state space is getting learned. And once certain state space has been learned, the exploitation is being done and action plan is being pitched from the graph. And that action plan serves as the first part of the action plan that needs to be carried out in the environment to reach the goal. Now, the rest of the action for generating the rest of the action plan, LLM agent called an action plan generator is being queried, and it comes up with a certain action plan. Now, this action plan, the first part and the second part is combined together, and the whole action plan is executed by the executor in the ScienceWorld environment, and the action observation sequence is getting recorded. So based on this action observation sequence and the feedback, I mean the reward is actually converted to natural language feedback in the environment. So those feedbacks, those trajectories are being used by a learner agent to generate a set of beliefs or learnings about the environment. So these learnings are again getting used by the action plan generator in future queries to the LLM to improve the plan generation. So these are certain plans, these are certain actions like look around, open door to kitchen, go to kitchen. So these are certain actions that the action plan generator can take. And these are certain learnings that are generated, like agent should open the door before going to a place. Okay. So initially, what it tried to do, like the door to the kitchen was closed, just trying to directly move into the kitchen. Okay. So after getting some feedback from the environment or the observations, so it learned like the door needs to be opened before moving into that place. So once this particular learning is there generated within the memory, so from next time onwards, it's always going to open the door before moving into a place.
By the way, I love this diagram so much. Like this really talks about the multiple memory abstraction spaces that I've been trying to build also. This is one space, state space graph to store the transitions. This is another
Yeah,
space, which is the reflections. And then you can put both of them together to get your action plan. And
yeah,
based on this state space graph, you do both rule-based traversal, which is basically the exploit, which counters the fact that LMs only exploit, I mean better match. And
yeah,
here you do LM based heuristic. So I think this is an awesome diagram. Like for those who don't know, this diagram was the one that after I look at it, I was like, I got to talk to this guy. Yeah, and so Swarna is here
yeah.
today. Yeah, it's such an ingenious method. Like, could you go more about into the insights of how you like discovered or how you thought about doing this? Like, I'm interested to know like what went through your mind when you built this.
Yeah, sure. So basically, when I started experimenting with LLMs to attack this problem, so I thought initially, like, if you are going to supply all the required information to the LLM, like all the knowledge about the environment, what are the different actions that can be taken, okay, everything about the environment. Uh, Even if the context, the prompt is very long, the LLM probably will be able to come up with a correct plan because of the attention mechanism. But when I started experimenting with that, I saw like as wrong. Okay. So even if we supply a very accurate information to the LLM, like what are the different objects, environment, and how to traverse from one uh, area to another area, the LLM in most cases was not able to come up with a correct plan. So So that time I realized the LLM are a very shallow reasoner. Okay. So they can reason up to maybe 2, 3, or 4, 5 steps at max, not more than that. Okay. So I was using that time GPT 3.5 and in some cases GPT 4. Um, so I realized like using like a LLM along with textual memories, it's not going to work. And along with that, like there's a limitation in the context then. And the next thing is like, so I had a very limited budget. Okay. So I have to reduce the context length. So I cannot supply a lot of information within the LLM prompt. Okay. So I have to figure out a way where I have to, reduce the prompt size and, generate an accurate plan. And also I cannot do a lot of calls to the environment. I mean, sorry, the LLM. So there is one way like we can take one action, get the observation and the learnings of the environment, and ask the LLM to predict the next action. Okay. So in this way, like iteratively, we can do a generate an action plan. But in that case, also I found out like it's going to take a lot of calls to the LLM. Okay. And also the context length will be relatively similar if you are going to generate the plan at one go. So it's going to increase the cost. So somehow I thought like if you are going to iteratively generate a plan, we have to somehow store the uh, plan which worked earlier in some way. So after thinking, like I found out like the best way to store the knowledge about the environment, like which actions worked earlier, is a state space graph. In that way, you can represent like which action resulted to which state and which action actually worked, like got the reward. Okay. So once I built the state space graph, I thought like why not apply the MCTS logic to do a exploitation balance and do a exploration in the state space graphs as well as exploit whatever is known. So in this way, I just thought about combining both these things and come up with this idea. So it's basically optimizing cost as well as addressing the shallow reasoning capability of LLM and reducing the number of calls to LLM. So all those things added to this idea.
I think that's really cool. Like you see, sometimes constraints cause us to innovate. And in this case, the context length constraint cause you to, hey, I need to store more things elsewhere. And then you thought of the state space graph. And
Yeah,
yeah, the reflection is more like, hey, LM keeps doing something wrong. how can I imbue some expert knowledge to it without being too handcrafted? Then that's where this
Exactly.
learning. I really love this. So I think Swarna, do you have any more important slides to cover, or could we just end on this slide today?
Uh, yeah. Yes. Action plan generator is a LLM agent. So it basically generates the the action plans during the random exploration. But sometimes it happens like while generating an action plan, uh, it gets stuck into a specific local goal. So the one that was at the beginning of the slide, let's say there is a goal of boiling a water, okay, and while boiling a water, so there is another sub goal, like you have to focus on the water or a specific object that you're trying to boil. So focus is a specific action. Now, while focusing on different objects from the environment, it found out like if you focus on the wrong object, it's going to give you a strong punishment. You're going to get a negative reward. It's a -100 reward. Now, that learning is being added in the reflection memory, okay, while exploring the uh, environment. So once that specific learning gets added to the memory, from next time onwards, the LLM just tries to find out how to focus on the right object instead of actually finding the water to boil. Okay. So sometimes it gets stuck to this local objective. So in order to that, so what I did intermittently, so I'm asking the LLM to create a long sequence of actions to explore and know more about the environment. So it's basically a random exploration, but that's not very frequent. It's very infrequent. So there is a probability of choosing this exploration. So it's basically sigma by ln of n exploration. N exploration is the number of times the random exploration happened. So
Interesting.
every
Because
time,
by prompting it to explore, it can come up with random sequences of actions already.
yeah. So
Interesting,
this is
interesting.
only because like the LLM is getting stuck in some local objectives. So that time I didn't know like how to alleviate that. So probably there are some better ways to alleviate that, but I thought like sometimes this random exploration works. I mean, when you are doing the random explorations, probably it's going to go to the kitchen and maybe turn the sink on and find some water. So once it finds some water, so that becomes part of the memory. And then once it finds the water, then it goes back to the original, task or original goal of boiling the water. So that's how you're like biasing the LLM using in context prompting to uh, like focus on the actual objective, not on the sub goals.
But how does the LLM know what actions are valid in the future? Because like, you go to a different room, you get different objects to interact with, which you only would know with the observation at that state. Like if you ask it to generate a random sequence of actions, there's a chance that many of them would be invalid, right?
Exactly. So in the action plan generator prompt, so I am supplying the set of actions that are actually possible in the environment. Okay. So there is a parameter called environment which I'm passing. So in the environment, this is the objective. This is the task that needs to be carried out. Okay. So these are the prior axioms. So this is the constant part, and these are the set of actions. So it's being given in this way. So the one action can be
Okay.
activate object,
So
close
basically,
object.
if the oh, you already gave it all the actions, all the possible actions, including the objects at each room in the prompt already for this exploration prompt.
Exactly. So these are the actions and these objects. OBJ is a parameter. So the OBJ can be replaced with the actual objects that are available in the room. So the objects are available in over here. So you can create a combination with this and this. So obviously there are a lot of actions, but we just parameterized it in this way so that the text length is smaller.
Yeah, I understand now. So actually, this one is like giving a little bit of the ground truth to the agent, right? Because you are giving all possible objects here. I mean,
Exactly.
one better way would be if we have a way to do some random sampling without knowing beforehand what are all the objects. Like maybe what could be done is if you want to have a random agent, basically when taking any observation, you just ask it, do any action randomly. So it will be more closer to ground truth where the agent only knows what objects there are in that room that he is in or it is in, rather than giving every single thing to the agent like that. I mean, to be honest, it's just an implementation detail. You could do whatever you did with multiple prompts as well at every action, but this is more economical because with one go, you get all the actions.
Yeah. No, see, this is these action set we are getting from the environment object. Okay. These are the possible set of actions that can be taken. But what are the objects in the environment? So uh, that actually we are not, getting from the environment, or it's not getting hard coded within the prompt. So that is part of the belief areas. I mean, so here, like, we are getting basically while exploring the environment. So it's going to get what are the different, like after getting the observations, it's going to get what are the different objects available within that room. Okay. So those actually consist of the available objects that can be acted upon. So it's basically learned from the environment while interacting with it. Okay. And of course, like it changes based on the location of the agent.
Oh, so these belief axioms are basically updated on the fly, right? As what the agent
Yeah,
knows. Oh, then
yeah,
then this
yeah,
is
yeah.
realistic. Yeah, then this is realistic. Cool.
Okay. So reflective learner. So this is basically generates the semantic learnings about the environment. So the learnings are generated in this format X, Y, Z, where X and Y are entities, subjects, or objects, and Y is the relation between them. Okay. So in this format, all the learnings about the environment are generated. Like the one learning that I have shown in the first slide is like the agent, in order to go from one place to another, the agent needs to open the door. Okay. So that is one learning that was generated. So experimental environment, I already explained, like it's an interactive environment, a huge state space size. It's not visible at the beginning. So I tested the agent against 7 different problems. And for each environment, the agent runs for several episodes. In each episode, like the agent is initialized in the start location in the hallway, and the whole search process proceeds from that initial position. And after the agent tries multiple actions, the rewards are added together, and the cumulative reward is getting calculated, and it serves as the metric for measuring the performance of the agent. So these are the results that I have also shown on the paper. So use thermometer, measure melting point. So these are different tasks that I have to carry out in the environment. So there are certain RL methods, DRRN, KG2C, CALM. So, and there are some generative language agents like Secan, React, Reflection, Clean. So these matrices are already reported in this paper, the Clean paper. And I have, so the agent that I built, it's named as NeoPlanner. And you can see, like, based on the rewards, the total rewards it has got in the environment, it almost solved all the tasks. Like out of the 7 tasks, 1, 2, 3, 4 tasks, it has fully solved. So if you get the reward as 100, it means the total goal is solved. And 3 of them, like it has almost solved the task, but it has not fully. And also, if you see the number of interactions with the environments, it's pretty much less compared to the RL methods. So I haven't written the number of interactions for these methods, but of course, it's pretty much less with respect to the RL methods.
Very nice, very nice. Yeah, I always believe RL is too slow. LMs are much faster to learn. And this LM with knowledge from memory is really a big improvement across all previous methods.
Exactly. So discuss, probably we have already discussed these points, like RL methods perform poorly if there are no signals found, like delayed reward environment. And LLMs can select better action plans, like in context prompting based on the semantic knowledge of the environment. Uh, but they also struggle, with exploration and converge to local goals that I have already discussed. Now, NeoPlanner combines both of the best of the both of the worlds and like came up with a combined solution. Uh, so this is like so initially the agent started with no learnings, and once it started exploring the environment, it generated some learnings like some semantic learnings about the environment. Like thermometer in kitchen can be moved to inventory. Agent can move between kitchen, living room, hallway, art room, bedroom, workshop. So these are simple things about the environment that are used in the future tasks uh, to better come up with the action plan. So what are the scope of improvements for this? So as I said, like one of the important part of this work is like, important limitations of this work is like, it tend to overfit and quickly getting started in local goals. So in the boil task, like, as I said, like focusing on the wrong object causes environment to reset. That is one learning that was generated. Now the LLM tries to find out the right object to focus instead of finding water, during the random exploration. So I solved this by intermittently adding, random exploration in the LLM prompt, like asking the LLM to generate long sequence of actions without any specific goal. But I don't think that's the ideal way of solving this. Probably there is some other way around, like where we can, guide the LLM to on the original goal instead of getting stuck or going on loop on the local goal. Probably breaking the task into subtasks and hierarchically solving it might alleviate the issue. Like in order to boil the water, like first you have to find the water and then you have to focus on the water. So these are the two different subtasks. So finding the water should be the first priority. So in this way, like if you can break the subtask and then solve the subtask and then combine them hierarchically, probably that will alleviate this problem.
Sounds like what TaskGen is trying to do.
Yeah. Right, exactly.
Yes.
So next is like sometimes like the plan doesn't follow the ideal shortest action plan that we usually, like we as a human usually do. Like if you are asked to boil, we just go find the water and put it in a container and put it on the stove and boil it. Okay, but here like what happens, like in like for the boil task, there are certain actions like pick up sodium chloride, mix sodium chloride, and maybe go to the greenhouse. But these actions come in between. Okay. This is because like during the random exploration, these actions are tried, and after trying these actions, probably it found the water. Okay, it went to the kitchen and turned on the sink and it found the water, and that finding water gave him a very strong reward. Okay. Now, while updating the state space graph, it was like recording the full trajectory, including these irrelevant actions, and it increased the value of the full trajectory based on the reward that it got at the end of the trajectory. So that's why these irrelevant actions are getting picked up from the state space graph. So this can be solved probably like some kind of state space pruning or state space shortcutting, where in order to like reach to a particular goal, probably like these irrelevant tasks may be shortcutted in some way, and like finding water, like the action that finds the water may be taken directly from the initial step. And so next is the memory management. So when the LLM goes on solving the task, it creates the belief axioms or the reflective learnings about the environment. So it just creates the whole learnings in the form of text, and it stores in the memory. Now there is a limit of the memory, maybe like it can keep 20 or 50 learnings at a time. So any new learnings it has like append, like some learnings has to be deleted, or some learnings has to be updated. But I think there's a better way of doing memory management. Like we can keep a set of learnings and create the embeddings of those learnings. And based on the task, like we can select most relevant learnings using a RAG. And I mean, not RAG, by just comparing the embeddings and select the best set of memories from the whole set of memories. In this way, like we don't have to limit the set of learnings into a very small set. And also like the relevant memories that we can fetch will be more contextual with the task, with respect to the task that we'll be solving. So this type of memory management probably we can use. So that's all from my side. So any more questions that you have?
Yeah, thanks so much, Swarna, for the wonderful presentation. And I think we all learned quite a lot from you. So just to recap upon what I mentioned at the start, which is like how does the brain like do planning efficiently, or at least not, because initially we were talking about MP hard and um, intractable compute for planning problems. It does seem like the way ahead will be more LM based heuristics to help to filter the search space a lot, and storing these learnings so that we can bias our agent to, head towards the more promising paths in the future. So this is one way of doing it. I think just as a segue into like our discussion, we will spend about 5-10 minutes discussing. Uh, I think this is just for one agent that keeps learning. If let's say we were to change the environment, it's likely that we need a population of agents so that we don't have this agent with all the baggage of what he has learned to prevent that agent from doing something new in the new environment. So all these things about improving the state graph, reflections, all this for this one agent may not be the full solution if the world is changing. Like we might need a population of agents and so on, right? But um,
Exactly.
I think at least for ScienceWorld, this way of continual learning is very effective, and I'm pretty impressed with the results that you have gotten. I mean, I myself am not a true believer of RL, so if you could replace the value function there with something else, because value functions take quite long to learn, and especially if a sparse reward, you probably won't get the value function of 1 anytime soon. Like you will take quite a while. If you could use
Yeah.
some other forms of distance metric, like maybe number of items versus number of goal items, that kind of metric, maybe that might be better than just using RL. So stuff like this. So with that,
Yeah.
I'll
So
yep. Oh yeah. Sorry,
yeah,
can
right.
answer first. Yeah.
Exactly. Like, see, RL, it's very difficult to learn. Like, we're going to need a lot of samples, and if rewards is sparse, it's very difficult. Like, but my idea is to like, whenever see in the real world, the real world doesn't give us any reward, so they just give us observations. It's up to us, like we humans, how we interpret them. It's a reward or a punishment. So I think like in certain environments, RL can be effective. Let's say a baby when starts learning to walk. So during that time, uh, the baby has a lot of area of experimentation. Like he or she can experiment in the environment. Okay, and it's a continuous space. Okay, so basically there, the reward or the punishment is getting converted from the error signal. Okay. So if you are going to lose a balance, so that's going to serve you as a punishment. So you can convert this into RL problem. So there, the reward or punishment is going to be dense in those spaces. But in certain spaces like planning or decision making, that might not be the case. So my idea is to, whenever we are getting some reward, or at least we are going to interpret some observation as a reward, let's exploit it. But if you're not going to get some reward in a sparse environment, in a sparse reward setting, then we have to have some alternative way to model the environment. Okay. So one interesting thing that I got from one of your work is like the fast and slow learning. So there we have built one network to predict next-based action. So it's a self-supervised learning, right? Uh, the
You
neural
mean
network
my,
that
my
we'll
work
be
on
using.
learning fast and slow? Yeah,
Yeah,
yeah.
yeah,
So
yeah.
we use the state transition to predict the next action. Yeah, using self-supervised learning. That's correct.
Yeah, that idea I found very interesting. So actually, I was thinking like instead of building a network from scratch, why not use a small LLM? I'm sorry, not small LLM, small language model, and fine tune it using a LoRa adapter, okay, parameter efficient tuning, using the same self-supervised way. I mean, just it will just predict the trajectory. What's the next best action in the natural language space? And like the LoRa adapters are very lightweight, maybe 50 MB or 100 MB in size. And for each different environments, like we can create a separate LoRa adapter, and we can use the same small language model as the base model, and we can load the LoRa adapters for different environments like a filter glass. Okay, or maybe we can use multiple LoRa adapters and maybe we can combine the output, and maybe we can at the end we can create a kind of a router or a decider combiner, kind of ensemble
Yeah,
learning.
I think those
Yeah.
are those are possible ideas. The main idea is that you learn continuously from your environment. That's the main idea. Self-supervised
Yeah,
learning is just a very efficient way of learning. And so as your external memory storage of state space graphs, I think those are very important. This way of
yeah,
continual learning, continuous changing, is very important as we want the agents to adapt.
exactly.
Yeah. So maybe with that, I'll just open the opportunity for the rest to ask any questions, if any. Yeah. So please go ahead. I know we've been talking quite a lot.
Yeah, I like the lore idea a lot, but I think the main gist of like the TaxGen framework would be that LoRa adapters, even in their like more specialized niche of maximizing that performance that you want, would be kind of like an abstraction space. Like you would have one level of the LLM where the LoRa adapters handle that kind of filtering, and then you could also have another abstraction space which could be more generalized knowledge, and you could run whatever memory graph you wanted based on that. You have all these kind of like LoRa filters feeding outputs and information to kind of like a summarizer agent or whatever you wanted to use that could basically take those summarizations of the outputs and kind of add it to this like kind of what would you call it, semantic memory that's much more generalized and abstract. So it would kind of be like more of like a guidance memory and therefore another level of the abstraction. That's the way I would go about it. I also think that I really like your project a lot, especially the math. The math is really cool. But I think the memory side of your state graph could really, really improve from a semantic memory format, just because you have this state space graph and you're able to traverse it pretty efficiently with the LLM exploration. The only issue is, like you said earlier, it's very undynamic, and you can
Yeah,
get a lot of kind of like garbage memory that kind of get built up in the memory. So being able to separate like the observations that are relevant, like your idea you were saying, the embeddings and stuff would be great for that. And then separating that and then having a separate semantic memory where you can just feed your current observations into the semantic memory as summarizations so that you get the best of both worlds and you minimize the amount of useless information that gets stored in the memory pipeline, basically, is the way I see it.
exactly. So that's a very good idea. Like, yeah, I was also thinking about continuing in this path in our future work. Memory management is one of the main thing like that we need to work upon. And yeah, like addressing the dynamic environment, so that is also a crucial thing. So that also like you have to think about, like how to modify the state space graph based on how the environment changes. Yeah.
Yes. I think I think overall this is a great idea, like of how to update the memory dynamically. Could you go back to that graph again? The entire flow chart of the agent. Yeah, I think it would be nicer to discuss while that is at the background.
Okay. Yeah, just a minute. This one, right?
Yeah, so I think the future way ahead for this kind of dynamic environments is that like we will need some form of adaptation of the state graph to the environment. And basically this means that like whenever something changes, okay, this will update the state space graph and including deletions.
Yeah.
And as what you were saying also, you know, in the fast and slow architecture, this for mine, this is actually the slow architecture. The fast architecture is actually this LM agent. This LM agent can be trained to make action plans based on current state and goal state. Yeah, using self-supervised learning. Yeah, you
Right.
could train the LM itself. So you could train both ways. Like you could train the prediction by this LM directly, and you can also train the external memory augmentation. Yeah, this is like fine-tuning. Yeah, it's just that for
Yeah.
most use cases right now, just doing this alone, just doing external memory, just giving right external memory is good enough to boost performance right now already. Yeah, but the
Yeah.
performance will definitely be improved if you can also fine-tune the LM even more. So I do
Yeah.
like this diagram a lot, and your reflections on this is also another way to bias the generation. If you could add
Right.
in another form of memory, what would it be?
See, this learnings, I would say, it's a semantic memory. Okay, so it's a very generalized rules about the environment, how the environment works. So another set of memory that are being supplied in the action plan generator is like the action observation sequence, and it's the most recent trajectory of the action observation sequence. So that I would say it's a part of the episodic memory. But I'm not storing the episodic memory in a stricter sense, like that's being stored in other works. So probably like we need to figure out a way to store the episodic memory efficiently. Maybe to add a temporal component to it so that the sense of time or the trajectory is being captured within the memory. So those kind of probably that will be useful for dynamic environments also. Like if you have the temporal component in the memory, and if the state changes in some time in the future, so it can map with respect to the time. So I'm just thinking out
I
aloud.
understand.
So
So basically, right now, your previous action and previous observations are all not fed into the agent, right? Right now,
yeah, so this action
is it?
observation sequence, yeah, it's being fed into the action plan, but the most recent action observation sequence is only fed there. I mean, it's not the whole part. Only the last calls action observation sequence has been fed here. So we are not explicitly
Understand. So
storing this sequence.
got it. So only the last action, and this means that if some action at the earlier part could influence the later part, that kind of relation is not captured right now,
Yeah,
and that could
yeah,
be inserted for better performance. Yeah.
yeah,
I like it. Actually, this is the same as subtask completed in TaskGen, where you store past input and output for the actions. And I
yeah,
do think this could help to bias decisions in the future also, like knowing maybe you are doing the task of boil water. Knowing you have boiled water in the past would already mean that you don't need to boil it again. Like if you had known
yeah.
it. Yeah.
Right, right.
If not, you
Yeah,
have to rely a lot on your state to encompass the fact that you have boiled the water. And I think in
exactly.
ScienceWorld, most of the time the state is enough, right? You don't need the sequence of actions.
Uh, Sequence of actions where?
Like this action observation sequence, like even without this action observation sequence, the agent is performing quite well in ScienceWorld, which also means that ScienceWorld doesn't need that information because the state is enough for the agent to decide.
Yeah, state is enough, but here like see in the action plan generator, like we are just supplying the current state and the previous action observation sequence. So this previous action observation sequence is going to help the agent decide like what are the some actions might be uh, failure or might get the agent divert from the goal. Okay. So let's say it tried, so let's say the boil task. Let's say it tried going to the kitchen. Okay. Now, in the first set, the the agent just tried entering the kitchen without opening the door. Okay. So there it got a failure message. Like you cannot go to the kitchen because the door is not open. Okay. Now, after getting this information, this is not directly going to the generated learnings. I mean, in the semantic memory. Okay. Now, in the next run, if you return this of the action observation sequence to the action plan generator, it will immediately know, like, in order to move to the kitchen, you have to open the door. So that it doesn't make the same mistake again. So that's going to help improve the action plan on an immediate basis. But once the action plans are generated multiple times, like 3-4 times, then the whole action observation sequence is getting cumulated and it's sent to the learner agent, and it generates generated learning, and it generates a generalized learning about the environment. Like you cannot go to a different room without opening the door. So from next time onwards, like it's going to use that semantic memory and it's going to take the correct action. I mean, open the door before going to a room. But that's how like immediate action observation sequence might help to filter out the irrelevant actions on an immediate basis.
Very nice. Yeah, Derek, you have anything else to add before we end today?
Yeah, I don't have. Yeah, Derek, please go ahead.
Yeah, no, I like what you brought up about the generated the learner element. It's basically doing what I was saying earlier about the abstract, the semantic memory and all that. It's already doing that. But yeah, moving forward, if you could like expand on that and make it more dynamic, I think you get a lot more performance. But yeah, I do say how you already have that kind of integrated into the other agents.
Yeah, right.
Okay, then, if nothing else, it's been a long session, but it's a very informative session. And I think this is one part of Swarna's life work as well. He will definitely be improving, and I hope to work closely with him to build a very performant agent that can really just adapt and learn very well from its interactions. Swarna's work has shown that using LLMs imbued with special memory structures and special pipelines like generating learnings and so on can already improve the performance on a difficult environment, the science world environment, by a lot. Like a lot is like at least 100% over past SOTA methods, and even more than reinforcement learning. So it shows that, if we want to do more higher level planning, we have to go beyond just going by rewards. We have to go into different forms of memory. And I think this work is a step in the right direction. So yeah, before we conclude, Swarna, any final thoughts or insights you want to share with everyone?
I don't have anything else specifically. Just like I wanted to explore the task general because I was very interested about like breaking the task into subtasks, because I think that is one key improvement that we can implement in this architecture. Because if we are able to, as I said, like we are able to break the whole task into subtasks, then probably like we can avoid that getting stuck into the local optima or the local task. So probably that one I'll be exploring, like how we have did in the task chain. Yeah, that's interesting.
And I also will be looking into how to incorporate state graphs as part of memory in task gen. So there's a lot of synergy in this, and I look forward to like more collaboration. Yep. Thanks so much, everyone, and have a good day. Yeah, bye.
Thank you, John. Thank you, Derek.